Okay, let's start the second part of the second day. And our first speaker is Persi Diaconis from Stanford, and he will speak about enumerative theory of the loose model for random permutations. Please.
Thank you, Alex, and everyone. This is a talk about probability distribution or enumerative combinatorics for a class of non-uniform distributions on permutations. But I want to start a little bit before that. Many problems in combinatorics can be said in this way. You have a finite set, X, and you have a statistic, a function from X into R, say, and then you can ask the question, what's the size of the set of all X such that T of X is some value little t? And one of the themes that's happened recently is that people are refining this question to slice the set X by a statistic S, say, and ask what's the size of the set of all X such that T of X is T, and that S of X is say some value little s. And the way we say that in probability language is in the following way. Well, first of all, what's an example? Pick a permutation at random, and suppose you fix its cycle type. How many inversions does a typical permutation have, and what's the distribution? Or suppose you look at the set of all graphs with a given number of edges and a given number of triangles, and then you pick such a graph at random and ask for the chromatic number or the number of other features of the graph. In probability language, we say, what's the conditional probability of, say, S of X given the second statistic T. A theme that's extremely popular in the last 10 or 15 years is by tilting the measure. Instead of, what I just said is a special case of this, instead of working with the uniform distribution, you can work with the measures tilted toward various values. And so one works with a measure, a probability distribution on the set X, which is theta raised to the T of X power, and then there's a normalizing constant to make it sum to 1. And here, for example, theta is between 0 and 1. And if theta is 1, of course, that's just the uniform distribution. But if theta is a half, that distribution will be quite concentrated over the minimum value of T of X. There are dozens and dozens, maybe hundreds of papers about two special cases. One on permutations. One is the Mallows measure, in which the statistic is taken as the number of inversions. Tilt the statistic by the number of inversions. And a second very well-studied measure is, because of genetics, is what's called the Ewan sampling formula, where the statistic that is taken is the number of cycles of the permutation. And any reasonable question about permutations under these two measures, in particular, the number of cycles, the number of fixed points, the descent structure, the whole descent pattern, the length of the longest increasing subsequence, any of the classically studied statistics are well understood. The distribution theory is well understood under these measures. So that's background. That is one of the things that's happened in probability when enumerative combinatorics is said that way, is looking at non-uniform distributions. And what I want to tell you is that today's talk is the following. Is a very simple, widely used measure. I'll motivate it in a second, but it's simple enough I can just say what it is in simple way, which is I have n weights, and they're going to be positive numbers, theta I bigger than 0, and think of putting those weights in an urn and withdrawing them one at a time without replacement, each time picking a weight, a ball, with probability proportional to its weight among the balls remaining. So if you pick out all the balls, that generates a permutation, and of course the order that you pick them out in depends on the weights. And that measure on permutations, which now has n parameters, theta 1 up to theta n, is called the loose measure. And it's very easy to write down what it is. If sigma is a permutation, written sigma 1, sigma 2 in one line notation, and if W is the sum of the weights, well, what's the chance of getting sigma? Well, you have to pick sigma 1 first. That the chance of that is theta of sigma 1 divided by W, and then you have to pick sigma 2 next, and the chance of that is theta sigma 2 over W minus theta of sigma 1 because you removed it, and then theta sub sigma 3 over times W minus theta sigma 1 minus theta sigma 2, etc. So that's the probability density of the loose measure. And the questions we're going to be talking about are the natural ones. Pick a permutation from the loose measure, and what does it look like? How many fixed points does it have? How many cycles does it have? What's the descent structure or other permutation patterns? Or what's the length of the longest increasing subsequence? And I'm happy to tell you that all of these questions are open. We can prove some things, but we can't answer any of these questions. And I hope somebody in the audience will get interested and make some progress on them. I want to offer some motivation for the study of the loose measure. So let me begin. There are many different places where it occurs. Luce is Duncan Luce, who was a mathematical psychologist, and psychologists study for 100 years. They study ranking. So here are 7 tones, rank them for loudness. Or here are 10 shades of red, rank them for brightness. Or familiar other thing generating permutations is you ask people, here are 5 different kinds of chocolate chip cookies. What's your favorite, next favorite, least favorite? So if people generate rankings and lots of applied situations in many places in the world, people vote by ranking a slate of candidates. And so you might have a population of people who are generating rankings. And Luce had the idea that each candidate, each object has a weight, and you rank them by this kind of ranking procedure that I just said. Actually, he has a beautiful, simple set of axioms that says that any measure on permutations which satisfies these natural axioms has to come from this family. But I mean, that's one place where the loose measure is used. A place that I've written about and I'm interested in is in poker tournaments. For example, every year there's something called the World Series of Poker, and suppose that the final table, which might have 7 players at it, starts, and each player has some number of chips, and it's of interest what's the order, the elimination order of those players. That is, which player is eliminated first, which player is eliminated second, and which player remains who will have all of the chips. And it's very widely used. You can imagine that understanding, so first of all, the player with the most chips actually just by poker lore has the best chance of being the last eliminated, and the player with the least chips probably will get eliminated first. What people do is let theta I be the amount of chips of player I at the start of the game, and then This loose measure is used to settle, that is, big stakes poker players often don't gamble for all the money. They say, well, let's take $10 million and split it up, and then we'll gamble for 1 million that's left. How do you split it up? Well, according to the chance that you come in first, second, or third. And those chances are very, very frequently assessed using the loose measure. And in the world of poker, that's called the ICM, iterated card model. And I'm not going to say more about it, but there's an enormous applied literature, and it's very widely used in poker circles. If you want to read more about that, I wrote a paper I like with Stu Ethier, and it's called Gambler's Rune and the Iterated Card Model and the ICM. So that's a second motivation for studying this measure. It's used by people. A different motivation is in horse race betting. So if you're mathematically inclined, you think, well, can I make money by studying the statistics of horses and the track and the riders and the conditions? And no, you can't. That is, even though you can do something, the track takes 17% of the money, and no statistics overwhelms that kind of thing. But there is a procedure that works, and it's widely used, somewhat widely used, and it's the following. The people who bet at the track do a pretty good job of what's the chance of horse I winning. But what they do a bad job of is what's the chance of horse I coming in second or horse I coming in third. And in the track, you can bet on a horse to win place, that is come in second, or come in third, win place or show. And the people do a bad job of figuring out what the chances of a horse coming in third. And so what you can do is go to the track, look at the amount of money that's bet on horse I just before the betting closes, and use those as theta I, and then figure out what the distribution on permutations is, and then calculate with an app what's the chance of horse I coming in third. And maybe 2 races out of 10, those odds are sufficiently out of line with the way people bet that you can make money even though they take 17% of the money. And that has a large applied literature on it, and people use the loose model to go from theta I to sigma. A different wonderful application is, I'll call it the Cetlin library, although it has many other names. Cetlin is the great Cetlin of Gelfand Cetlin and many other things. Cetlin was working in a library science institute for a while, and he floated the following problem. Suppose you have, at the beginning of the day, the librarian puts out n books in order, 1, 2, up to n. And each time a patron comes along and picks up a book labeled I, and the chance of their picking book labeled I is theta I. And then they look at the book, and then they put it back at the left end of the row. Okay, so that's a process that goes on. And what I've just described is a Markov chain on the permutations of n. Each book has a weight, and then you pick book I with probability theta I, and then move it to the top. And that Markov chain has the loose model as a stationary distribution. And the Markov chain is widely used in computer science applications for what to do with large disks. And it's pretty widely used. Here's yet another motivation, another place that the loose model occurs. And I'm going to use probability language for a minute, but then I'll stop that. So suppose I have n weights and I order them, that's without loss, theta 1 up to theta n. And suppose I pick independent exponential random variables where the mean of the exponential is theta I. Okay, so I just pick n independent exponentials, standard exponentials times theta I, and so I just let x1 up to xn be in those exponentials. Now, of course, they're random, so they might not come out in order 1 up to n, even though theta 1 is biggest, they come out in some order. What's the chance that the order statistics are sigma? That is that x sigma 1 is the biggest one, x sigma 2 is the second biggest one, x sigma n is the smallest one. It's exactly given by the loose model. So that's a little theorem. So that's another place, and I'm not going to have time to motivate why that's interesting, but it's quite important in nonparametric statistics. As an example of the kinds of weights that are interesting, here's my last probability example. Suppose I have standard exponentials, mean one. So like E1, E2 up to En be independent random variables, which are exponential, each with mean one, and then order them. So I'll call E round brackets 1 the smallest, E round brackets 2 the second smallest, etc. Take the order statistics of this sample, and then ICECA2023, an Indian statistician, proved the following theorem. If you look at the spacings, the smallest one, the second smallest one minus the first smallest one, the third smallest one minus the second smallest one, look at the spacings between the order statistics. In fact, those are independent, exactly independent, and they're exponential, and the parameters are 1 over n minus I plus 1. So the spacings are these weighted exponentials, and so the statistics of spacings, and therefore all kinds of statistics, are well described. So the smallest of the values is a standard exponential over n. The gap between the second smallest and the smallest is an exponential over n minus 1. So the sum of these two is the sum of two exponentials, and that is, anyway, I will use the ICECA2023 weights as examples and things that are coming. So I hope that that's enough motivation. There's a non-uniform distribution on permutations, and it's widely used in lots of different applications, and I want to talk about its enumerative theory. So I have a few theorems, but the main point of the talk that I'm giving today is that you can prove theorems about this in some generality, and there are many questions that are left open, and I hope somebody will get interested in that. So let me start with an easy theorem. Let's look at the top k cards. So I'm in the situation where I have weights, theta 1 up to theta n, and without loss, suppose that they sum to 1. That'll make the formulas a little easier. And let's look at the chance that the top k cards, because after all, the card that's the card that comes out first, the first letter of the permutation, is likely to be the one with the largest weight. I mean, there's randomness, but so what's the chance that the permutation starts sigma 1 up to sigma k? Well, under the loose measure, that's theta sigma 1 over 1, theta sigma 2 over 1 minus theta sigma 1, etc. This is the loose probability that the measure starts out sigma 1 up to sigma k. Now, if n is a little bit large, sampling from a large urn with and without replacement, it shouldn't make very much difference if you think about it. And so consider sampling from the urn with weights, but with replacement. So then the chance of it starting sigma 1 up to sigma k would be theta sigma 1 times theta sigma 2, theta sigma k. Just the independent sample. And a theorem that makes specific the heuristics that I talked about is this. If you look at the difference between these two measures, sampling with and without replacement, it's small if k is small and the weights aren't too crazy. And this is an inequality. It's not so easy to parse. This is the smallest weight, the next smallest weight, etc. And that's in the exponent, so that has to be small in order to make this okay. So meanwhile, if you pick the ICECA2023 weights, if you pick these weights, probability proportional to I, what you can see is that the two measures are close to, I mean, there's an explicit inequality, but the two measures are close together as long as k is small with respect to square root of n. And so a takeaway from this little theorem is that the top cards are essentially independent with probability proportional to the weights. So that's easy and straightforward. I want to look next at the bottom k cards. And so let me begin with an example. Suppose that the weights are theta 1 is unnormalized. Theta 1 is 1, theta 2 is 2, theta n is n. So it's likely that the first card I pick out is n, and then, the next card I pick out is something like n minus 1. You pick out the big weights first. And so I'm asking what card's left at the end? What's the chance that the last place in the permutation, is some number? Well, it's likely to be low, and well, it's part of the theory we're going to develop. The chance that instead of fluctuating and having very much randomness, the chance that the last card left is 1 is actually around a half. It's 0.516, and this is in our example, this is the probability that the bottom card is 1, 2, 3, and it's pretty rare that it's 5. That's a limiting theorem when n is large. So here's now going back to general weights. That was an example. So let me consider this way of making a sequence of problems. Consider a sequence of weights, theta 1, theta 2, theta 3, and let's take them ordered. Okay, so I have an infinite sequence of weights. I'll only use the first n, but then n is going to get large. And make a power series. F of x is the sum from I equals 1 to infinity of e to the theta I times x. And if that's infinite, it's infinite, tough. And I'll take x to be positive. So that's a function f of x. So I have general weights, and I've introduced this function f of x. And our theorem is the following. Let x naught be the smallest x, such that f of x is less than infinity, and let sigma n be a random permutation from the loose model with theta 1 up to theta n. Okay. Then sigma n converges in distribution. That'll say that we're only going to look at a few coordinates. That's all convergence and distribution of a sequence of random variables means. If and only if, first of all, this radius of convergence is finite, x naught is finite, and at the radius of convergence, f of x naught is infinite. And that's necessary and sufficient condition on the weights for convergence of a few coordinates. And finally, if this condition holds, that is, if f of x naught is infinite, then the chance that the last card is labeled A1, the second from the last card is, well, this is the joint joint distribution of the k bottom cards. Sigma n1 is A1, sigma 2 is A2, A1 or AK or any values at all, is given by a formula, and it's an integral. If you have k cards you're thinking about, it's an integral over some kind of k simplex, and involves exponential terms. So it's not easy to look at that formula. Let's look at the simplest example. Let me take the loose weights. Theta I is I. And so you expect the bottom card to be 1, as I said. Well, what the formula says is that when n is large, the chance that the bottom card is 1, for example, is integral 0 to infinity. There's only one parameter, e to the minus x times this product from j equals 2 to infinity times this product of exponentials. Well, change variables in that. So that's the integral from 0 to 1 of the product from 2 to infinity of 1 minus y to the j dy, and do that integral however you like numerically, and that's where that 0.516 comes from. So the main point I want to make is, I'm interested in these questions, but the main point I want to make is you can do math on the loose model. It's not, it's not completely beyond thinking about. And I'm going to give one more example, and then I'm going to quietly surrender. You can prove theorems about P sigma for somewhat, you have conditions, and there are counterexamples if the conditions don't hold, but you can prove theorems about P sigma. So moving back toward the usual topics of this conference, here's a last example, which is with Shorroff, Chatterjee, we can do the distribution of inversions. So people probably know that if you pick a permutation at random from the uniform distribution, the number of inversions is around n squared over 4, and it has a certain standard deviation, and the distribution of the number of inversions around n squared over 4 follows the bell-shaped curve. There's a central limit theorem. Well, now I'm going to look at the loose model. So I've got theta 1 up to theta n positive numbers. Pick sigma from the loose model. Let I of sigma be the number of inversions. Okay. Well, it has a mean, and it's easy to see that the loose model has this feature that if you look at cards 1, 3, and 5 and ask what's the chance that they're in any of the 6 relative orders they can be, it's as if the other cards weren't there, and cards 1, 3, and 5, their distribution is from a loose model with parameter theta 1, theta 3, theta 5. The loose model restricts in a nice way. And so from that observation, it's easy to see that the mean of the number of inversions is the sum over I less than j of theta j over theta I plus theta j. Just there it is. That's the mean of our statistic. And the variance, well, it's again not too hard. You have two things, so it's 4 cards you have to think about, but it's pretty easy to do too. The variance has a formula, which is a kind of nice symmetric formula. I'd hate to do higher moments, but you probably could if you needed to. That's not the way we proved our theorem. And the theorem, and I'll try to parse this for you, but let me first state it as a theorem. So pick sigma from the loose model and look at the number of inversions, and subtract off the mean and divide by the standard deviation. And what's the chance that that normalized statistic is less than or equal to t? Well, it should be like the bell-shaped curve here. Phi of t is the area to the left of t in the normal distribution. So that's the natural approximation to this statistic. And the theorem gives an explicit bound and says that the quality of this approximation is bounded by 3 terms. C is a universal constant. It doesn't depend on the thetas, and we could say what it is. And there are 3 terms in the bound, but the thing I haven't told you about is this A term, but it's an explicit bound is the point. And A is the difference between the variance of the statistic and n, and then you take the positive part of that. And so A, of course, positive part might be 0, in which case 1 over A is infinity, and this bound says nothing. But for natural choices of weights, this is a useful bound. And in particular, if your weights are such that the variance of the statistic are bigger than n to the 8 over 3, then the right-hand side is tiny, and and you have a normal approximation to the statistic. These conditions work in particular for uniform weights, which is a classical theorem, but also for the Sukhatmi weights and any weights that are kind of nice and not too wild. Okay, so that is again trying to make the point that you can prove theorems of the kind that we study in probabilistic combinatorics for the loose model. And if you wanted to read all kinds of references to the motivation I did and see proofs of these theorems, there's a paper that Saurav Chatterjee and Jean Kim and I wrote, and it's called Enumerative Theory for the Cetlin Library, and it's just appeared in the Journal of Algebra. It's on the archive. It's on my homepage, and there we are. So I have a question for the moderator. Mr. Moderator, can I ask you a question? When am I supposed to stop?
No, not yet. You have 20 more minutes.
Great.
If you want.
That's very good. No, I have things to say.
I don't even have an idea to warn you about the end coming soon.
Okay.
Lots of time yet.
I'll stop. I'll stop on time. I'm sure, but I just where I am right now is I introduced the loose model, which is an n-parameter non-uniform distribution on permutations. I try to motivate that it comes up in applied work, and I try to motivate that you can do math about it. Okay, so now let me get a little bit closer to some of the topics that have been talked about here. Richard Stanley gave a nice talk on his favorite posets. Well, here's a little theorem that's in our paper. Of course, you can ask, suppose, theta 1 is bigger than theta 2 is bigger than theta n, so the most likely permutation is the identity, that you pick 1 first and then 2, but there's a lot of randomness in it. And you have what's the probability of a permutation sigma, and that's a function of sigma if theta 1 up to theta n are fixed. And that function is monotone in the weak Bruja order. That's a natural thing if you think about it, if you switch pairs out of order, but that's a little theorem. A second thing I wanted to say is the following. So we heard things about log concavity, and it's well known that under the uniform distribution, the distribution of the number of inversions is a log concave function. The probability that you have j inversions is a log concave function of j, and you can ask that question for the loose probability. Now, what we proved is that the number of inversions follows the bell-shaped curve, okay? But the bell-shaped curve is as log concave as you can get. And of course, that's a limiting theorem, but I want to remind people that one of the ways that people prove log concavity, Lisko and Richman in particular, one of the ways that people prove log concavity in tough problems is by proving a central limit theorem, a local central limit theorem with a good error. And once you have the central limit theorem, when you know the normal distribution is log concave, and then you check the first 1,000 cases on the computer. And that strategy has been used. Anyway, it's a reasonable question. Pick theta 1 up to theta, fix theta 1 up to theta n. Is the loose probability of the number of inversions, is that a log concave function? And I tried it in some little examples. It seemed to be, and so maybe somebody might get interested in trying to prove that. I'm not going to stop talking, but I'm going to stop the share, and I'm going to talk this way. So there's an important large, healthy, open area that's related to this, and it relates to the talk we just heard two talks ago. The loose model, the Zetlin library moved to the top, is the most special case of what I call random walk on the chambers of a hyperplane arrangement. And so we just heard a nice description of some class of hyperplane arrangements. We'll take any hyperplane arrangement, that divides space up into chambers, and there are faces and etc. An important geometric ingredient for a hyperplane arrangement is the Tits projection. That is, given a face and given a chamber, there's a unique chamber adjacent to the face, which is closest in the sense of passing through the fewest number of hyperplanes to reach it. And that's called the projection of the chamber on the face. Well, that gives a semigroup structure to the chambers, and what you can do is make a random walk, and the random walk is the following. You have an arbitrary measure on the set of faces of your arrangement. Pick a face, you're at a chamber, move to the chamber adjacent to that face. Pick another face, there it is, move to the chamber adjacent to that face. So you march around on the space of chambers from using this projection operator. If your arrangement is the braid arrangement, then the chambers are indexed by permutations, and the most special case of this random walk is the Zetlin library. And so what I've just been talking about is the following. Take any random walk on any hyperplane arrangement, or if you like, there are lots of people, Ben Steinberg and Anna Schelling, who have made extensions of that to other semigroups. So take any random walk on the chambers of a hyperplane arrangement. We have very good control over those random walks. We know the eigenvalues, we know rates of convergence, we know all kinds of things about those random walks. The thing we don't know is about the stationary distribution. And what I've been telling you about is the problem of understanding the stationary distribution of these hyperplane walks. And we developed that theme in the paper that I just cited. There are some examples where there's been one or two examples where there's been work, but there are infinitely many hyperplane arrangements and lots of natural walks on them. And understanding natural enumerative questions for the stationary distribution are completely open math problems. And what I've just tried to tell you about is that even in the simplest case, the case of the Zetlin library, I should say the stationary distribution for general hyperplane arrangements can be described through a sampling without replacement scheme. That's one of the theorems in a paper I wrote with Ken Brown, there's a similar, a little bit more sophisticated, but hardly, description of the stationary distribution in terms of sampling without replacement. So if these problems about sampling without replacement are of interest to you, there are many places to look for special cases. And those walks are due to Pat Bittiger, Dan Rockmore, and Phil Hanlon, and then Ken Brown and I wrote a paper with an early development, but there's a lot of literature on and all of that is discussed and with references in the paper. Okay, so on that note, I am quietly going to stop, even though there may be more time, but maybe there are questions, and if not, well, we can all take a few minutes off. Surrender. Thank you.